Presentation. Our final speaker is for this session is Jamie Macbeth, and the title of the paper is A Broader Range for Meaning the Same Thing, Human Against Machine on Hard Paraphrase Detection Tasks. And just a reminder to go to talk-Macbeth Slack channel if you want to ask questions. So you can go ahead and share your screen, Jamie, whenever you're ready.
All right, how's that? Can everybody see my screen and hear me? Or
yes.
Maybe some people can?
Yes.
Yep.
At least one, yeah.
Okay, good, okay. Yeah, so those of you who've heard me talk before or know me have often seen me bring up the idea of paraphrasing as an important task for natural language understanding and for cognitive systems. And I think it's important because language is understood in the face of linguistic variation, the fact that there are so many different ways of saying the same thing. Paraphrasing is a special task in natural language understanding because in comparison to other tasks, I think there are many tasks where you can, in natural language understanding or story understanding, where you can calculate a deduction, a sequence of language-like expressions that show what you know and thus solve the problem that you're facing in natural language understanding. Paraphrases are, I think, in many ways different because there's a degree to which everything you need to know is right there in the expressions themselves and you don't need a deduction. And to be able to talk about two natural expressions meaning the same thing, like we talk about when it comes to paraphrases, is kind of a hint there that maybe part of the meaning representation that we're using, this same thingness, is something that's not in the natural language expressions at all. Either way, clearly paraphrasing tasks have something to do with meaning representation. In our paper, paraphrasing generation and determination is the cognitive task that we focus on in exploring issues of meaning representation. And what you're looking at is output from an inferencing and paraphrasing system from the 1970s, part of which we used in our studies, and I'll get to that in a moment. Oh, okay. Let's see. Okay, I want to be able to use my arrow keys. As part of our exploration, we theorized about two competing paradigms that cognitive systems might engage in when doing things concerning paraphrasing. And pardon me while I read from my slides, but there's some awkward wording here that I want to make sure I get right. So one is the service alignment paradigm. And so you can say one approach to meaning representation is to say that meaning exists entirely within language. There's no non-linguistic component. There's nothing outside of language to meaning. And you can say paraphrases are simply equivalence relations between lexical and syntactic language forms. And then your task when doing things with paraphrases is building systems under this view is to find and extract sets of language expressions that comprise that meaning equivalence relation that you can transform one natural language expression onto another. Another paradigm that competes with this that is one that we call, I'm trying to be able to see my slide. I need to move this. Okay. Yeah, so the deep understanding paradigm. In this paradigm, part of meaning representation of an expression consists of structures and processes that are actually not part of the expression itself. And more deeply, the structures in question are not simply logical assertions that use the words in the original expression, but they're some kind of language-free cognitive symbolic structures. They correspond, there's a correspondence between these structures and surface language expressions, but they may not resemble those language expressions and don't necessarily correspond one-to-one with them. So Patrick Winston talked about the idea of inner language. Others talk about mental models and mental imagery. This is the idea that we're trying to get at when it comes to meaning representation with this paradigm. Looking again, our cognitive task is determining, detecting, or recognizing a paraphrase relationship between linguistic items. Let's formalize it that way. And our main claim is that the deep understanding paradigm is the real deal. It's a consequential part of forming meaning representations, particularly for human cognitive systems. This is not a new claim, but we think it's important in a time when big data and deep learning systems are supposedly building their own representations when doing natural language understanding tasks. And to support our claim, here was our methodology. Sorry, I wanna move it so I can see my own slide. Okay, great. We basically compare systems that we saw as service alignment systems and deep understanding systems on paraphrase tasks. So that was our methodology. Okay, one preliminary thing that I want to talk about is the idea of surface difference metrics that were used both in our alignment systems and in our studies. So X and Y, one distance metric, and I think a lot of people use this distance metric, the idea of lexical edit Levenstein distance. Basically, it's like the familiar edit distance that we know, but instead of working in characters, it works in complete words. So it's a minimum number of additions, deletions, and substitutions to transform one sentence to another sentence, but on the word level instead of character level. Another one is Jacquard distance, and basically that is an intersection over union sort of measure over the set of words. It's a unigram metric over the set of words in the sentences X and Y. You can say the cardinality of the disjunctive union, but it's basically the words that are in neither of those sentences divided by the number of words in neither of those sentences divided by the number of words in the union of those sentences. And we also use the blue metric, bilingual evaluation understudy. Originally, this metric was for machine translation systems. I'm not going to go deep into it, but basically say that it's like the Jacquard distance. It's a unigram metric, but it keeps better track of duplicates and penalizes better for those kinds of things. And so it's a little bit more fine-grained than Jacquard metric. So first I want to talk about the paraphrase corpus that we built that fit into the deep understanding paradigm. The paraphrasing system that I showed you in the first slide is a system called MARGI, which Chang built at Stanford in the early 1970s. It's a classic example of the deep understanding paradigm, in my opinion. It uses what claims or what strives to be a language-free meaning representation built from complex combinations of conceptual primitives called conceptual dependency. On the left is a conceptual dependency structure representing a particular meaning, which you'll see surface expressions of in a moment. Now, I said that this system is language free, but there appear to be words in there. What's going on? Let's say that this conceptual dependency system isn't perfect, but I do want to point out that this ingest conceptual primitive, just as an example, represents something, it's supposed to represent something more abstract in general than the actual English word ingest normally means. It was used for any sort of act in which an object substance goes inside the body of an animate actor through any sort of means, whereas ingest, people usually mean it taking food or water into the body. In this case, it's being used for the act of breathing. So it is more abstract in general than the meaning of that word. We actually have the original code for MARGI's paraphrase generation system, which we used. We made some enhancements to it, and based on this this structure here, we generated a large number of paraphrases. So here are paraphrases of that idea that we generated. Basic ideas that John died because he could not breathe. I'll give you a second to read them over. And what I want to point out is that these paraphrase pairs have a very high degree of lexical and syntactic difference. If you look at them, these three pairs, only one or two words are common in expressing this idea. And so this is what we were able to achieve with this system called BABEL that came from the MARGI project. So we were able to generate 432 paraphrases of the same idea. We made some modifications and enhancements to the original system which, you know, they were using 1970s technology, so it's understandable. But based on the 432 paraphrases of this idea, we use that to generate 90,000 or so paraphrase pairs. All these pairs are paraphrases, or we think they are paraphrases. We'll see more later. But we wanted to use these in our studies. Okay, so that was the deep understanding paradigm corpus. Now for the service alignment part, we use this corpus called the Microsoft Research Paraphrase Corpus. It consists of about 6,000 sentence pairs annotated with paraphrase, non-paraphrase classification. So some of these are paraphrases, some of these are not according to the classification. And this data set was constructed through an alignment process. Let me say a little bit about that. So the broad idea of the way that MRPC was constructed was they took advantage of the fact that at the time, early 2000s, there were a lot more news articles. And the idea was that different news articles about the same events are going to contain sentences describing the same events, but those sentences might be slightly different. So maybe there are paraphrases in there. So they exploit these clustering algorithms used by the aggregator websites, and they scrape sets of topically and temporally related news articles that they call clusters. And they take articles in a cluster supposedly describing the same event around the same time, and they try to match sentences that come from those articles using lexical edit distance metrics. So it's important that I mentioned that earlier. Each candidate pair of sentences was required to share at least 3 words in common. So they would compare sentences, see if you could find 3 words in common in those sentences, of course, without stop words. So the idea is two news articles about the same event. If there's a sentence in one and sentence in another that share 3 words in common, it's very likely that they're talking about the same, I guess, sub-event within that story. And so they're likely to be paraphrases of each other. The other constraint was that the sentence pairs were required to have lexical edit distance between 8 and 20 edits. So they're looking for sentences that are describing the same thing, but aren't exactly the same. It's kind of a weird window of lexical syntactic similarity that they're going for, but that's the hope, is that if there are a few words in common, they describe the same event in the story. But then if they're, you know, if there's a certain lexical edit distance between the sentences, then maybe they're a bit different syntactically, probably, maybe lexically somehow. And then they got experts to do annotations on each of these sentence pairs. Some of them end up being paraphrases, some of them not. Here's an example of a paraphrase sentence pair from MRPC. Let me give you a second to read it. So a lot of what happens apparently with news stories is that people will take an existing news story, an existing article, and edit it and update it very slightly and republish it. So the alignment procedure comes up with lots of sentence pairs that maybe look like this. This is kind of an extreme example. These sentences are nearly exactly the same, but just rearranged syntactically. In fact, they use exactly the same words. They have a Jacquard distance of 0 and an edit distance of 23. So when you use alignment, you get certain kinds of interesting sentence pairs. That's all I'll say about that for now. Okay, so those are the corpora that we use in our studies. Now, what about recognizing paraphrases? So for the deep understanding paradigm, our example was the human. We did human participant studies on Mechanical Turk, where people viewed sentence pairs from BABEL, from MRPC, and a set of attention check pairs to make sure that people aren't just answering randomly. So, you know, it's crowdsourcing. We started with 100 participants, and then we evenly sampled over for the BABEL sentence pairs, we evenly sampled over the Jacquard distances of the BABEL sentence pairs for those 100 participants. And then for MRPC, we had a random sample of pairs annotated as paraphrases. For the attention check pairs, we basically created these pairs of sentences that were also from this benchmark called GLUE that MRPC is part of. But we always made sure that the sentences were way off in terms of topic, in order to catch people who might be just answering randomly. But then we wanted to make sure we had a good coverage of BABEL sentence pairs that had high levels of lexical and syntactic difference. So we added some more participants to the study. We sampled the set of BABEL sentence pairs that had the maximum Jacquard distance of 0.957. And then we also sampled all of the BABEL sentences that had BLUE score less than or equal to 0.4. So the BLUE metric, by the way, is inverted. High values of the BLUE metric mean that the sentences are very similar. Low values mean that the sentences are very dissimilar. So it's the opposite of Jacquard in terms of the polarity. But overall, we had 208 participants in the study. I just wanted to explain why there was a weird number in the study. Now, okay, now what about so that's the deep understanding paradigm for our recognizer. What about the service alignment paradigm? For our recognizer for the service alignment paradigm, we use BERT. Lots of you have heard of it, I'm sure, the bidirectional encoder representations from transformers. This is not a talk about the centers on BERT and its behavior, so I won't go too deep into it, but it's a deep learning neural network system, general purpose architecture for natural language understanding. It can do lots of different tasks because it has this efficient pre-training part of its architecture over a huge data set, and then you can do fine-tuning using it for a particular task like MRPC. We used BERT base. There are different versions of BERT, like BERT large, but BERT base is fine. And BERT base has 100 million total parameters. And our BERT base was fine-tuned on MRPC, which has paraphrase, non-paraphrase classification. So it can look at a pair of sentences and try to classify them as paraphrases or non-paraphrases. One other thing I should mention. So for our studies with humans, we thought that rather than get just paraphrase, non-paraphrase annotations like what MRPC has, we decided to use this scale called the Semantic Textual Similarity Scale that was developed as part of the SemEval workshop series. And we had our human annotators use this scale, hoping that it would give us finer grained information about what's going on with our paraphrases. So you can see it has a finer range than just paraphrase or non-paraphrase. It's completely equivalent, mostly equivalent, roughly equivalent, and so on. So you'll see in the human annotations that they have this scale. Okay, so let's talk about results. So for human classifications, one thing that we were interested in is, okay, we have these BABEL sentence pairs. The MRPC sentence pairs, they have expert classifications for whether they're paraphrases or non-paraphrases. Are our BABEL sentence pairs really paraphrases? We think that they're all paraphrases, but we want to make sure. And the answer, based on the human classifications that we got from Mechanical Turks, is that yes, they are. You can see over on the left, very, very high percentage of them are in the completely equivalent category. We also looked at a subset of the sentence pairs that had the maximum Jacquard distance of 0.957 that we called BABEL max here in the table. And those also had a very high percentage of completely, of participants saying that they were completely equivalent, and even greater than the MRPC data set, where it seems like a lot of people thought the MRPC paraphrases were mostly equivalent. And this seems to be an artifact of the techniques used for MRPC. But our paraphrases really do seem to be paraphrases. Okay, so next, let's look a little bit at the BERT classifications, particularly of the BABEL sentences. So for small Jacquard distance, BERT classifies all pairs as paraphrases. So we're suspicious here. We think our belief going into this is that BERT is likely going to be using using lexical and syntactic similarity to make its judgments about whether or not two pairs of sentences are paraphrases. So this is kind of our embedded hypothesis in this. For lexical edit distance of greater than 8, though, for the BABEL sentences, which we believe are all paraphrases. So anytime that BERT says that BABEL sentence pair is not a paraphrase, we see that as kind of an error. For lexical edit distance greater than 8, it falls to 80%. And for max Jacquard distance of 0.957, the accuracy falls to 61.7% for BERT on the BABEL sentences. And the correlation between BERT classifications of BABEL sentence pairs, we did a statistical correlation between the BERT classifications and the Jacquard distances of the sentence pairs, and we found that that was statistically significant. So our suspicions are true. So to illustrate this further, we generated the human performance to BABEL to BERT performance on the BABEL sentences. So what you're looking at here is a plot of classification accuracy as a function of lexical syntactic difference represented by inverse BLEU score. So remember, large BLEU score means the sentences are very similar in terms of lexical and syntactic difference, and small BLEU score means that they're not very different. In the red, you have classifications that humans gave to BABEL sentence pairs. The SCS scores that humans gave have been scaled for comparison to BERT, so they've been scaled from 5 down to 1, and in both cases they've been averaged over equal-sized bins, and so you can see the dramatic effect that humans are actually processing mean representation that's independent of lexical syntactic difference of the sentence pairs. You know, the red part of the plot is up at 1 for all of the sentence pairs, no matter what the BLEU score was. Whereas for BERT, once the lexical syntactic similarity falls below a certain level, it seems to be a coin flip about whether it thinks that the sentences are paraphrases or not. Okay, I wanted to say one more thing about this. Distance measures in MRPC. So one thing we're also interested in is BERT's behavior just a reflection of the training data? So we compared the Jacquard distances for the 67% of the original MRPC pairs, about 6,000 of them or so, that were annotated as paraphrases against the 33% that were not. So some of the MRPC pairs were not paraphrases, and we found that both Jacquard distances and edit distances were statistically larger for the non-paraphrase pairs in MRPC. Although it wasn't a dramatic difference, it appears that there may be quite a bit of bias built into the BERT model due to the way the MRPC data set works. Okay, so suspecting that I'm low on time, let me summarize. Our main claim was this deep understanding paradigm is real. It's a consequential part of forming meaning representations for cognitive systems. And our supporting evidence was that we found that generally these alignment-based systems diverge significantly from humans on deep understanding-based paraphrase recognition tasks. And particularly as a function of lexical and syntactic difference in the sentence pairs, as we just saw. So being really out of time, I'd just like to end there. I'd like to thank Neil Goldman, who worked on the original Margie project, for providing the code for BABEL that allowed us to do this project. And I wanted to thank our student collaborators from MIT and from Smith College. And I'll cut to questions now.
Great, thank you. Okay, so just a reminder, folks, go to the Slack channel to ask any questions. It looks like there was some discussion, not really questions, about ingest. So Michael Cox mentioned that ingest also covered shooting with a needle.
Yes. Thank you, Michael.
Sentences. Pat Langley points out that sentences with arguably different meanings could map onto the same CD encoding.
Yes, exactly. So in this study, I just talked about generating paraphrases from a single CD representation. If you go the opposite way, which is also an important part, many natural language expressions will map onto the same CD representation, and those natural language expressions are paraphrases. So that's how you would, the theory is that that's how people are detecting paraphrases, by mapping natural language expressions of various kinds and finding that, oh, when I have my non-linguistic meaning representation of this sentence and this sentence, they're the same. So yeah, I agree with those comments. One thing about ingest, so in some of our work, we've been exploring how ingest might be further decomposed into what in CD was called P-trans, for those of you who are familiar with it. P-trans represents movement from one place to another, and some kind of containment primitive. So ingest might be able to, you might be able to decompose that even further to movement from the outside of an object to the inside of an object that's contained after movement.
Jamie, sorry, can you repeat the last bit? You broke up.
Oh, I'm sorry. I was saying that ingest could be decomposed into a movement of one object being outside of another object to being then inside that object. I hope that got through. So it could be decomposed into a P-trans and some kind of containment primitive representing that now your location is in there. Now the injected stuff is inside me.
Got it. Thank you. Okay, so let's go to Hillary asks, Hillary Harner asks, how do you identify and rule out bad paraphrases? Booty call is a terrible paraphrase of butt dial, although the individual words are basically synonymous with each other. This feeds into the larger question of how you deal with idiomatic languages.
Aha, okay.
Lots of great examples there, analogical ones too. Anyway.
Yeah. So this is a question that comes up a lot. So how do you, in these systems, how do you handle, okay, the crop is showing there, but in these systems, how do you handle complex social situations like, oh, that term was offensive to me for certain reasons, although it means the same thing as this other term. So generally speaking, I think, you look at these kinds of representations and you see stuff that's funny, like for example, inside the CD representation for the sentences we were just working on, there's this thing there that says health val -10. And so this is kind of, I don't really believe that people's understanding of how their health works, or whether they're alive or dead, is just simply a numerical scale from -10 to +10 or whatever it is that they had. So my thing is that when it comes to complex social interactions, that what you see on the right there is an example of a script that's part of the restaurant script. So in this tradition, those folks did work on larger decomposed structures that represented complex social interactions. And so that's where we're going generally in terms of decomposing more complex, sort of, especially socially socially complex language and representations. I'll just say that.
Okay, let me just check for, we have time for one more question from Michael Cox. Have you been able to look at James Allen's plow to see if it handles the paraphrase task any better?
No, but I will do that. I didn't know about that system. I will check that out. Thank you, Michael. I'll get in touch and get connected.
Great. Okay, so we're right at the end of time. So thank you, Jamie. Thank you to all the presenters.